This one has produced the most stunningly precise results. I'm talking about quantum electrodynamics, the first true quantum field theory. Quantum mechanics is perhaps the most unintuitive theory ever devised, and yet it's also the most successful in terms of sheer predictive power. Simply by following the math of quantum mechanics, incredible discoveries have been made. Its wild success tells us that the mathematical description provided by quantum mechanics reflects deep truths about reality. And by far the most successful, most predictive formulation of quantum mechanics is quantum field theory. It's the best description we have of the fundamental workings of reality. And the first part of quantum field theory that was derived, quantum electrodynamics, is the most precise, most accurate of all. Quantum field theory, QFT, describes all elementary particles as vibrational modes in fundamental fields that exist at all points in space and time through the universe. Quantum electrodynamics, QED, provides this description for one such field, the electromagnetic field. The pillars of QED are the description of the behavior of the EM field and the description of the behavior of the electron via the Dirac equation. We covered the Dirac equation last time, and you really should watch that episode first if you haven't already. Now, before we start thinking about vibrating quantum fields, or even fields at all, let's talk about vibrations. Anyone who's ever strummed or shredded knows that a stretched string vibrates with a certain frequency when plucked. It also vibrates with an amplitude that depends on how hard you pluck it. A larger amplitude and/or larger frequency means the vibration carries more energy. At any point in time, every point on a vibrating string is displaced by some distance from its relaxed or equilibrium position. And that displacement changes over time as the string oscillates back and forth. Guitar strings are one-dimensional, but we can expand the analogy to any number of dimensions. In 2D, we have a membrane, like a drum skin. Everywhere on the surface of a vibrating drum skin, there's a displacement from the flat equilibrium state in the up-down direction. The 3D analogy is harder to imagine. Every point in space has some displacement in some imaginary extra direction, analogous to but not the same as a fourth dimension. For example, in a 3D room full of air, sound waves are oscillations in air density. That air density has an equilibrium value, which is just the average density, but at every point in the room, a sound wave can cause air density to oscillate to higher and lower values. We describe air density as a field because it has some value everywhere in the space of the room. And that's all a field is, some property that has some value throughout a space. Okay, let's go quantum. And let's go back to the string. If this were a quantum mechanical guitar string, then there'd be a minimum amplitude for the vibration that depended on its frequency. No vibrations with amplitudes smaller than that minimum could exist, and every larger vibration would have to be a whole number, an integer multiple of the smallest amplitude. This is exactly how light behaves, as was first realized by Max Planck and proved by Einstein. Light is a wave in the electromagnetic field. The electromagnetic field is similar to the density field in a room full of air. It has a value, a field strength, everywhere in the universe. That value is usually 0, but just like the string or the air density field, it can oscillate. The electromagnetic field is a quantum field, and so these oscillations have a minimum amplitude. The smallest possible oscillation above 0 is an indivisible little packet of energy that we call a photon. Quantum physics may have started with Planck's discovery of the quantum nature of light. However, the first full formulation of quantum mechanics was Schrödinger's equation, and it couldn't account for light at all. We touched on the reason for that in last week's episode. Basically, the Schrödinger equation is incompatible with Einstein's relativity. It can't describe things moving anywhere near the speed of light, and it implicitly assumes that forces act instantaneously. We also saw how Paul Dirac managed to find an equation describing the behavior of the electron that worked with relativity, the Dirac equation. However, understanding the behavior of light and its interaction with matter required a different approach. It also required Paul Dirac, again. That guy was a genius. Let me first mention another problem with the Schrödinger equation. It's terrible for many particle systems. It follows the changing position and momentum, and generally the physical quantum state, of every individual particle. But that's extremely inefficient. See, two of the same type of elementary particle are indistinguishable from each other. If you take a pair of electrons or photons in two quantum states and make them swap places, then nothing changes. Following the quantum state of every individual particle is like trying to do your finances by tagging and tracking the movement of each individual dollar. No one cares which dollar is which, we only care how many dollars end up in whose bank account. But bean counting this way is not just inefficient in quantum mechanics, it gives the wrong answers. A given quantum event or interaction can happen in multiple different ways, and the probability of the interaction depends on correctly counting those different possible ways. If you try to track individual particles, you're at risk of double counting. You end up with multiple arrangements of particles that are actually the same arrangement due to the particles being identical to each other. That means you get the wrong probabilities. Paul Dirac's solution was to not try to track the changing states of individual photons. Instead of quantizing particles' physical properties like position and momentum, as did Schrödinger, Dirac quantized the electromagnetic field itself. He imagined each point in space as being an oscillator, technically a simple harmonic oscillator, just like an oscillating spring. The oscillation at each point can be complicated, but it has to be built up from a number of minimum amplitude quantum oscillations, which is to say, photons. So Dirac described a space of quantum states, including position and momentum/frequency, like an infinite array of springs. His mathematics then kept track of the number of particles or quantum oscillations in each of these states. This automatically avoids double counting because the math doesn't even try to keep track of the movement of individual photons, only the shifting number in each quantum state. Dirac wasn't the first to come up with this idea, but he was the first to successfully apply it to describing electromagnetic interactions. He named the resulting theory quantum electrodynamics. He also coined the name second quantization for the process of counting the changing number of quantum oscillations, or particles, per state. Schrödinger's approach of tracking the changing quantum state of each particle became the first quantization. There's another reason this second quantization is better at describing the interactions of light and matter. See, Schrödinger's approach has no idea how to destroy a particle. All it can do is move particles around via their evolving wave functions. Yet in particle interactions, particles are created and destroyed all the time. An electron can absorb or emit a photon. An electron and a positron can annihilate each other and create two photons. And that can even happen the other way around. But the second quantization is all about creating and destroying particles. This new capability became essential for the description of subatomic processes. The resulting quantum electrodynamics describes the interactions of matter and radiation with stunning success. It is one of the most carefully tested theories in all of physics. For example, it eventually allowed scientists to predict, with incredible precision, the tiny difference in atomic electron energy levels due to electron spins, spins interacting with magnetic fields in the so-called hyperfine splitting, or spins interacting with vacuum energy fluctuations in the Lamb shift. It predicts the relative value of the fine structure constant to a precision of 1 part in a billion, No other theory in physics has done so well. Spurred by its success in describing electromagnetism, physicists soon extended the second quantization approach to other elementary particles. It required different rules for the fields. For example, the Pauli exclusion principle tells you that you can only have one fermion, so electron, quark, etc., per quantum state, rather than infinite particles in the case of the photon. Nonetheless, second quantization works for all elementary particles. That tells us something extremely important. Remember, this approach began with thinking of photons as oscillations in the electromagnetic field. So does this mean that all particles are also oscillations in fields? Well, yes, that's exactly what it means. In fact, every base elementary particle has its own field. It is its own field. This is the postulate of quantum field theory. Fields are fundamental, and particles and their antimatter counterparts are just ways in which that field vibrates. There's an electron field, whose oscillations are what we know as the electron and the anti-electron. There are fields for every type of quark-antiquark pair, for every type of force-carrying particle, so-called bosons, like photons and gluons, and of course for the famous Higgs boson, which is just an oscillation in the Higgs field. The calculations of QED and of all quantum field theory are about counting the number of ways a quantum phenomenon can occur. That's a challenge because there are infinite ways in which anything can occur. In fact, a huge part of quantum field theory is about taming the infinities that arise in any calculation. To do that efficiently, we are going to need another genius. We're going to need Richard Feynman. And we're going to need another episode of Space Time. Thanks to the Great Courses Plus for sponsoring this episode. The Great Courses Plus is a to the fundamental, the greatest geniuses of the modern era discovered the two keys to the fundamental nature of reality. Einstein's theory of special and general relativity had changed forever the way we think about motion, space, and time. And the emerging field of quantum mechanics had radically altered our understanding of the fundamental building blocks of the universe. Yet this year, 1928, one brilliant insight would bring these theories together and unveil the quantum fabric of reality. It would also predict the existence of antimatter. By the late 1920s, Einstein and Planck had already shown that light is a particle as well as a wave, and Louis de Broglie had shown that all matter has this dual wave-particle nature. Bohr, Heisenberg, Born, Pauli, and others pieced together a mathematical description for the weird nature of subatomic particles. Then, in 1926, Erwin Schrödinger wrote down his famous equation, the Schrödinger equation, which breathed life into this emerging model. It describes how these matter waves, represented as wave functions, change over time and allowed physicists to predict the evolution of quantum systems, such as the strange interference pattern in the famous double-slit experiment. Yet, everyone knew there was a problem. First and most obvious, the Schrödinger equation is totally incompatible with Einstein's relativity. In relativity, the dimensions of space and time are intrinsically connected and they flow into each other as frames of reference change. But the Schrödinger equation tracks the evolution of a particle's wave function according to one and only one clock, typically the clock in the reference frame of the observer. Relativity tells us that the passage of time depends on velocity, so the Schrödinger equation only works for slow-moving objects. That's a problem. Subatomic particles are often moving at close to the speed of light. The other problem with the Schrödinger equation is that it describes particles as simple wave functions, distributions of possible positions and momenta that have no internal properties. Yet we now know that many elementary particles have an internal property called spin. That doesn't mean that they're actually rotating, but spin does result in a sort of quantum angular momentum. For example, electrons' spin causes them to align themselves with magnetic fields, just like a rotating electric charge would. The axis of spin can point in different directions, for example, up or down. The discovery of quantum spin starts with an Austrian physicist named Wolfgang Pauli. Pauli realized that to explain electron energy levels in atoms, those electrons must obey a rule that we call the Pauli exclusion principle. It states that no electron can occupy the same quantum state as another electron. In fact, it applies to all particles called fermions. In the case of electrons in atoms, it suggests that we should only find one electron per atomic orbital, if we count each orbital as a quantum state. However, we actually observe 2 electrons per orbital, and so Pauli realized there must exist a hidden quantum state. Pauli introduced what we call a new degree of freedom internal to electrons, one that could take on one of 2 values. Let's call those values up and down. That would allow 2 separate electrons, one up, one down, to occupy the same atomic energy level, without occupying the same quantum state and therefore violating the Pauli exclusion principle. Other physicists soon figured out that this new quantum state represented spin, and the up and down degrees of freedom were the direction of pointing of the angular momentum axis. We now call these 2-component wave functions spinors. Now, it's okay to ignore spin in the old Schrödinger equation and get approximate answers. But when a magnetic field is present, spin direction becomes very important. So, for fast-moving electrons, and for electrons in electromagnetic fields, the Schrödinger equation gives the wrong answers. The problem consumed a brilliant British physicist, Paul Dirac. He wanted a fully relativistic version of the Schrödinger equation that worked for electrons. In a way, he started with relativity. He wrote down Einstein's famous equation, E = mc squared, but in its full form, including momentum. He then used quantum mechanical expressions for energy and momentum. The result was a huge mess, but Dirac stumbled upon a single, simple idea that caused the resulting horrendous mathematics to collapse into an incredibly simple, beautiful equation. That simplification required Dirac to expand the internal workings of the electron even further. Instead of having a 2-component spinor, up and down, as in Pauli's theory, he needed 4 components. Now, he had no idea what those 2 additional mysterious components might mean, but the resulting equation was so simple and elegant that somehow Dirac knew that he was onto something. The resulting Dirac equation describes the space-time evolution of this weird 4-component particle wave function represented by the symbol psi. It contains the marks of both quantum mechanics in the Planck constant and relativity in the speed of light. The Dirac equation perfectly predicts the motion of electrons at any speed, even in an electromagnetic field. It was a major victory, but it opened up even more questions than it answered. To begin with, what on earth were those 2 extra degrees of freedom in the 4-component electron? The answer came from trying to calculate the energy of the electron using this equation. It predicted something totally bizarre. It allowed electrons to exist in states of negative energy. If true, that would lead to some weird effects. For example, a lone electron moving in an electromagnetic field could keep releasing energy as light infinitely and sink lower and lower to infinite negative energy states. There was no bottom to the energy well. We know perfectly well that this doesn't happen. Dirac came up with an idea to explain this. We called it the Dirac Sea. Imagine an infinitely deep ocean of electrons that exists everywhere in the universe. These electrons occupy all of the negative energy states, all the way from negative infinity up to 0. The only time we can actually interact with an electron is when one has a positive energy, which would leave it sitting on top of the sea. This is where the Pauli exclusion principle comes back. If the energy states of this imaginary ocean are all completely full, then that one extra electron can't lose any more energy. It just floats on top of the sea. The idea of the Dirac Sea leads to its own weird predictions. Remove one electron from the surface, and it leaves a hole. That hole should act like a particle all by itself, a bit like an eddy on the surface of a pool of water. It would move around, it would have inertia, acting like it had the mass of the missing electron. It would also act like it had the opposite electric charge to the electron, a positive charge. And if a positive energy electron found one of these holes, it would fall in, annihilating both and releasing all of the energy bound up in their masses. Of course, there is something in our universe that acts exactly like holes in the Dirac sea. It's called antimatter, and Dirac had just predicted its existence. Now, the Dirac sea itself doesn't really exist, but it was one of the first attempts to describe something very real, the idea of a quantum field.